All right, good day, everybody. You should have received the packet for ocean acidification. If you don't have the packet, make sure you get one from the front of the room or from the sub, and you're going to be taking notes on the packet from the slides that you're seeing here. Okay, so you should have already watched the video that you see here. If you haven't watched the video, this is the time to stop and change to that video. I did share that with the sub, but if it's difficult to find, you can just go into YouTube and search for A Climate Calamity in the Gulf of Maine, Part 2, Acid in the Gulf. It's about a 5-minute video, so go ahead and watch that now if you haven't watched that already. Otherwise, we continue. And I just wanted to give you a reminder about the pH scale. This is what we finished with right before spring break. And, remember that the pH scale is something that measures how acidic or basic a substance is. So the lower the numbers on the pH scale, the more acidic. The higher the numbers on the pH scale, the more basic. If the pH is 7, that's neutral. So something like water would be neutral. Something like lemon juice, vinegar, battery acid, those would be acidic. Something like ammonia or Drano, those would be basic. So we had worked with some of those household items in the week before spring break, and this is just a reminder of what acidic and basic are. All right, and some terminology. What's the difference between pH and acidity? So pH is the scale that we were just talking about that goes from 0 to 14, and it describes how much acid is in a liquid. So it's a logarithmic scale that makes it easier for us to talk about big or small numbers. So in the case of pH, we're talking about small numbers, the concentration of hydrogen ions. All right. And the amount of hydrogen ions in a liquid determines how acidic it is. So we would say something is acidic if it has a high concentration of hydrogen ions. We would say something is basic if it doesn't and it has more hydroxide ions. All right. So what we're going to relate this to this week, everything that we've learned about pH and acidity, we're going to relate that to ocean acidification. So this is a term that is used by international experts to describe a decrease in ocean pH over the decades. And it's related to, it's related to climate change and to the increase of carbon dioxide in our atmosphere, because our oceans take up carbon dioxide from the atmosphere, and this is resulting in a decrease in ocean pH. Okay, so we call that process ocean acidification. All right, and ever since the Industrial Revolution, we humans have been creating more carbon dioxide, releasing that carbon dioxide into the atmosphere, and the ocean is taking up that carbon dioxide faster today than it has in the past, because there's more of it in the atmosphere, right? And this is causing the global ocean chemistry to change more quickly, and ocean systems are not adapted to this type of pH. All right, so it's causing some disruptions in the ocean systems. All right, so ocean acidification, right? It's caused by the uptake of carbon dioxide at the ocean surface. So where the ocean is interacting with the atmosphere, there is intake of gases from the atmosphere, and whatever gases are in the atmosphere end up getting mixed in with the ocean. Okay, this is causing that decrease in pH. So since the Industrial Revolution, like I said, there's been more carbon dioxide put into the atmosphere, therefore more carbon dioxide put into the ocean, and it has resulted in a decrease of the global average pH at the ocean surface of 0.11, right? That sounds really small, but that's a 30% increase in hydrogen ion concentration. So when you look at it that way, that's kind of a big increase of hydrogen ions. And an increase in those hydrogen ions is going to alter ocean chemistry. So why is that important? Right? Why should we be concerned with such a small change in pH? So many organisms are very sensitive to that small change in pH, and we'll talk more about that in a second. They're sensitive either to the direct or indirect change in the acidity in the marine environment. Okay, so by direct meaning like that particular organism is directly affected. Indirect would be that change in that one organism cascading through the rest of the food chain and the food webs. All right, so respiration, which is the breathing in of oxygen, the taking in of oxygen and releasing of carbon dioxide. Calcification, which is, excuse me, the building of organisms' shells or their skeletons. Photosynthesis, because carbon dioxide is something that is used as a reactant in photosynthesis. And then reproduction as well. That corresponds to the magnitude of changes in carbon dioxide concentrations in seawater. So you can see all of those things are relevant to life in the oceans. Breathing, creating glucose through photosynthesis, reproduction, making new organisms, calcification, like the building of their bodies. All of these things are affected by small changes in pH. Okay, so here's a little bit of the chemistry. So as carbon dioxide is absorbed into the seawater, it creates carbonic acid. So you'll see that in the first step here. If carbon dioxide goes into the ocean, it interacts with seawater, H2O, and it creates a new product, carbonic acid. And then this carbonic acid is going to release hydrogen ions, and it's going to create the bicarbonate ion and the carbonate ion as well as the hydrogen ion. Those hydrogen ions, this is what is causing the increase in pH. Okay, so what it's doing is also decreasing the concentration of carbonate ions because it's interacting with the hydrogen ions, and those carbonate ions are the building blocks for many marine organisms' shells and skeletons. So that's the problem we're going to be looking at this week. What is the effect of the decrease in concentration of carbonate ions when hydrogen ions react with carbonate ions to create the bicarbonate ion? How is that going to affect ocean organisms? All right, so the thing that we're looking, okay, so the ocean absorbs about a quarter of the carbon dioxide that we release into the atmosphere. That's a lot. All right, a quarter is 25%. All right, so as we continue to put carbon dioxide into the atmosphere, every time we drive, every time a factory is putting out exhaust, smoke into the atmosphere, we burn things, that's all released in carbon dioxide. All right, so do the levels in the ocean. So as we increase carbon dioxide levels in the atmosphere, we're increasing the levels in the ocean. All right, and at first, I remember when I was your age, scientists were happy about this. they said this is good. This is basically buffering the impact of carbon dioxide in the atmosphere because the ocean is removing some of this carbon dioxide. So the impact of us putting carbon dioxide into the atmosphere is being mitigated and lessened by the ocean absorbing some of it. But what they're seeing is this is impacting the ocean pH way faster than they thought it would, right? So that's the downside. That carbon dioxide absorbed by the ocean is changing the chemistry of the seawater, which in turn is affecting the food webs in the ocean. All right, now here's a chart that's showing over time they've been looking at carbon dioxide levels since the 1950s, and then in the 1980s, 80s and 90s, they started looking at the amount of carbon dioxide in the water, in the seawater, and the amount of hydrogen ions or the pH of the ocean water. So the red line is the carbon dioxide in the atmosphere. And you can see that's going up. It goes up and down, but the trend is really, very starkly going up. Okay. And so it started probably at about 320 parts per million. Is that parts per million? And now it's up. We're looking at this number over here. Yeah, at about 400. So it's increased from about 320 parts per million to about 400 parts per million. That's the carbon dioxide in the atmosphere. Now, the seawater carbon dioxide, it kind of goes up and down more drastically than the atmosphere, but you can see the trend is definitely up to where, maybe it was in more of down at the 350s, 325 to 350, and now the range is between 350 and 400. This is parts per million in the ocean, right? That's the green line. The blue line is showing the seawater pH, and you can see, again, it goes up and down with time, but definitely the trend is down. That's bad, right? So the downward trend is a bad trend. We want the ocean pH to stay closer to like 8.1, and it's getting closer to 8, which is a change of 0.1. But like we said, small changes in pH have great impact on the life in the ocean. All right, so how are these impacts seen in life in the ocean? So like we said, that cascading chemical reaction results in changes in the amount of calcium carbonate. And what does calcium carbonate do for marine organisms? Those are the building blocks for their skeletons and shells. So think of the calcium carbonate as Lego pieces in the building blocks of these organisms. If you don't have enough Lego pieces, you can't build the thing you're trying to build. All right, so that's part of the problem here. So where life exists in the ocean usually around the coastal areas, especially in the cooler regions of the ocean, it's super saturated with calcium carbonate, meaning there's a lot of it there. Okay, so it's really easy for these organisms to just grab calcium carbonate out of the water, build their little bodies, get on with their lives. Okay, so we can, we can see these shells all over the place. All right, but when we have ocean acidification happening and you have a lower pH, which means you have a lot of hydrogen ions around, that interacts with the calcium carbonate. And when it does that, it takes it out of circulation, right? So once the hydrogen bonds with the calcium carbonate, now it's like taking that Lego piece out of commission. You're not going to be able to use that to build shells if you're using it to bind with hydrogen ions. Okay, so it causes parts of the ocean to become undersaturated, to have less carbon dioxide. And now when those organisms are looking for calcium carbonate to build their shells, it's not there. It's like trying to build something out of Legos and you can't find the Legos you need to build the thing, right? So that's what these organisms are going through right now. All right. So it makes building and maintaining their shells and other calcium carbonate structures difficult. Which organisms is this affecting? Things like oysters and clams, sea urchins, corals, and calcareous plankton. All right. And you might think, okay, how is this affecting the rest of the ocean? Can't the rest of the ocean get along without these organisms? Maybe, maybe not. A lot of these creatures form like the bottom or the middle of the food web. Other organisms depend on these for their food, and so do we. We eat oysters, we eat clams. Some people even eat sea urchins. Okay, and then the other, like the fish that we like to eat those things, right? Okay, so it can also affect other fish as well. So certain fishes' abilities to detect predators becomes decreased. So they're not able to detect predators in more acidic waters. So when they're being approached by a predator, they may not be able to see or not see, probably detect is a better word, usually through scent or some other like electrical signals coming through the water. They're not able to detect the predator. Now, those organisms, those fish, are at risk. They get eaten, and then the food web may also be at risk. So the predators are going to benefit for a while until their prey is suddenly all gone because they've been eaten by all the other predators. Now there's no basis for their food in the food web. Okay, and we're going to stop here. I'm going to continue when I get back. We'll continue talking about the food web and talking about different types of fish and how they are affected by this whole process. Okay, so right now you can, I'll post this video into Google Classroom. So if you missed anything and you need to watch the video again, you can watch the video or you can look at the slides without listening to the video. Either way, it's fine. But we will continue this when I get back. I'll be back on Tuesday. Also, we're going to be doing a lab using shells and acid and see the effect of acid on shells. All right, so that's it for now, and thank you very much.